In the part B of the chapter 11, we are going to talk about the signal transduction along the axon, or we see along the neuron, how it happened and how the signal are sent from the cell body to the axon terminal. First, let's talk about the basis, the membrane potential. Remember when we talk about the rest membrane potential, we are talking the membrane are negative inside and positive outside, so that keep a potential that the membrane can be disturbed. And all the neurons are highly irritable, which means if there's enough stimulus, the membrane potential will change and it may generate an action potential, which we also call it as the nerve impulse. So those nerve impulse is always the same regardless of the stimulus. No matter how big the stimulus it is, the peak, the curve is always look like this, which is an action potential. And those action potential just travel along the axons by changing those charge along the membrane on the axon membrane, and it will just conduct this action potential to the axon terminal. In physics, there are a few basic principles about electricity. One is opposite charge attract each other. The positive charge attract negative one, and the negative one attract the positive one. And also energy is required if you want to separate those opposite charge across a membrane. So if those things just attract to each other, if you want to separate them, you need energy. And when the charge move towards another, and those energy will liberated. And if opposite charge are separated, the system have a potential energy. So just as the membrane potential, rest membrane potential, the positive charge are outside the membrane and the negative charge are inside the membrane. It's separated by the cell membrane, and thus give the cell membrane a potential energy, which make it ready. And once it stimulates, once it gets stimulated, those energy will released. So there's a few terms you want to know before we talk about the action potentials. One is a voltage. That is a unit, is a measure of a potential energy generated by those separate charge. If there's a larger potential energy, then there's a larger voltage. So what you see by volt or millivolt, those are the voltage, tell you how much potential it is to give the energy. Like the outlet on your wall, those are 110 voltage here in US here. Okay, so those are called potential difference or potential, or we just call it voltage. They are measured in voltage. Okay, so there is a charge difference across plasma membrane, and that's always about -60, -70 millivolt. So it just means there's some difference between the outside and inside of the cell membrane. If the charge is there's a greater difference, then it just means they're higher voltage. And the current is the flow of electrical charge. It can be electron, can be ions in our body between 2 points. Once those ion channels open on the cell membrane, those ions pass through it, that give a current, which is a current. And the thing that resists the current to go through, that is a resistant. Like the current go through the cell membrane, the cell membrane is to prevent that current go through it, that's a resistant. Only by opening the different number of the ion channel, it allows those ions to go through, and those ion flow, which is the current. So the cell membrane is work like a insulator. If it's a purely bisulfite lipid, it's a phospholipid, those are the insulator. And if is like an ion channel holes. Those are the conductor which allowed those electrical ions to go through it. In physics, the Ohm's law is saying that the current is equal to the voltage divided by the resistance. So the idea is the higher those resistance it is, the less current you will get. So less ions will go across the membrane. Or if you have a larger voltage, then the currents can increase if the resistance keep the same. So that is Ohm's law, and apply to the cell membrane. You can consider the cell membrane is a resistant part, and the voltage is a cell membrane potential, and the currents will be the ions go past the cell membrane. Most part of our cell membrane are the bilayer of a phospholipid, and that is an insulator of electricity. So the current, like the ions, cannot pass those layers here. At this location here, there's no ions can pass it. So it's an insulator and no current can pass through, but we do have some ion channels like this one here that allow the ions to go through, so the current can generate by go through those ion channels. And there's two main types of ion channels. One is a leakage, so there's no gated channel, is just a hole, a protein hole on the cell membrane. So those ions will just go through this channel freely. And the other type is gated. The gated one always have some controlled door on those ion channels to make sure once those ions go through, it's controlled by different conditions, either by binding certain ligands, or it may be opened if the cell membrane go to certain threshold. There are three types of gated ion channel in our body. One is chemically gated. Remember the chemically gated? In this picture here, you can see those channel here have a small receptor site, the small indentation here. That is a place to attach to a receptor as the acetylcholine receptor. Once this receptor receive a ligand by it, and this channel will open, then sodium and potassium can go through it. The second type is a voltage-gated channel. Those channels have a sensor that sense the cell membrane potential. So you can see here's a membrane potential, and it changed to another way, and this channel will be open. It's have a voltage sensor on those channels, so those are the voltage-gated. And the third type is a mechanically gated. So you can think it's just a physically can pull it open like this. It's normally for like a sensor for touch, or for the sensors in your inner ear. We have so many mechanically gated channel there, especially for the sensory organs. Okay, so those are the three types of gated channels inside your body. So here is a typical cell in your body, like this one. There's a big potassium. It's not one big potassium sodium. I mean, there's a lot of potassium sodium inside the cell, and there's a lot of sodium ions outside the cell. That's how the concentration look like at the resting stage. So the resting cell have more sodium outside, more potassium inside, and also it's negative inside, positive outside. That is a resting cell. Okay, for no matter which type of cell, it's negative inside, positive outside. So on that condition, those leakage channel keep on open, but gated channel, they are normally closed. So the gated channel, once they are open, if some ligand come in, neurotransmitter bind those receptors, open the channel, or because of the change of the membrane potentials, it will just make small channels, small holes on the cells, so those ions will just cross the membrane along electrochemical gradient. So the positive one want to go to the negative one, a negative place, and the lower concentration, the high concentration ions want to go to the low concentration. So which means the sodium want to go in by concentration, and if those channels open, then potassium want to go out by concentration as well. And also there's other ions inside and outside, and they may just go across those channels as long as their channels are open. Okay, so once the ion flow through the membrane, there's a current. A current will occur once those ions go in or out of the cell. And once the current change, then the voltage, the potential of the cell membrane will change. The cell membrane potential change, and those voltage change may open another series of channel again. The resting membrane potential is the potential cross-membrane of a resting cell. Resting cell, which means the cell is in the resting stage, are not stimulated. So for most of the cell, they are about -70, okay, -70 millivolt, and in fact, depends on which type of cell, they may range from -40 to -90. -90 is more like the muscle cells. So it's always negative, which means the negative inside relative to the outside. So in this condition, there's negative inside and positive outside. We call it polarized. So those are the polarized cell. It's a resting membrane potential. So the resting membrane potential is generated by difference in ionic makeup of intracellular fluid and extracellular fluid. The outside extracellular fluid have more sodium ions, and intracellular fluid have more potassium ions. And those difference together with the permeability of the cell membrane. So the different ion channels only allow certain kind of ions to go through it. That will make the potential of the cell. Extracellular fluid have a high concentration of sodium, and intracellular fluid have a higher concentration of sodium, potassium than the extra. And in fact, if you just see the intracellular fluid and extracellular fluid, each part of them are electrical neutral. Although we see it's negative inside, positive outside, we are talking about the small regions along the cell membrane. But in fact, there's a lot of sodium outside. At the same time, there's a lot of chloride ions outside to neutralize, to balance the whole thing. And the same thing inside the cell. There's a lot of potassium inside, and there are a lot of negative charged protein inside to balance. So inside and outside together is electrical neutral, but just on the small regions along the cell membrane is polarized. It's because of the potassium is more permeable. The cell membrane is more permeable to potassium, so potassium play most important roles in membrane potential. For the negative ions inside are those large ionic protein, and those are so large that cannot go out of the cell membrane. And the cell membrane is slightly permeable to sodium compared to the potassium, which is more easy to go out. There's a more leakage channel for the potassium. So the cell membrane is much more permeable to potassium than the sodium. So the potassium determines the cell membrane resting membrane potential. It's also quite permeable to chloride as well, but for the resting membrane potential is mainly maintained by the potassium ions. There are more potassium ions diffuse out than the sodium ions diffuse in. So in that case, if we just see the net change of those ions, it's a positive charged ions, which are those potassium ions go out. And once those positive charged ions go out, it gives a small current at this local region here. So it makes the inside of the membrane is negative and the outside is a positive. Once the the potassium go out, because there's a lot of potassium inside the cell, so they want to go out according to the concentration gradient. But however, at some point, then the force make the potassium go out from the chemical concentration is equal to the force for the positive charge potassium go out to the positive side of the cell, because that go to a same charge part of the cell membrane, so there's a resistance. Once those chemical gradient and the electrical gradient reach a balance, that's the time the resting membrane potential reach the resting potential. So that the end result will be the cell become more negative inside, and also it have this resting membrane potential established. At the same time, the sodium-potassium pump stabilize the resting membrane potential. This pump is use ATP. Every time consume 1 ATP, it will pump out 3 sodium and pump in 2 potassium. So in that case, it will just maintain the gradient of sodium and the potassium, and make sure it's high potassium inside and high sodium outside. So that give our resting membrane potential, which is negative 70s for neurons. Let's see a few review questions here. In a living neuron, which component provides resistance to current flow? The answer is A, the membrane. So just think through the current. It comes from the outside to the inside of the cell, which is sodium. The sodium go outside to the inside, and potassium go inside to the outside. It all cross the membrane, and that is resistance. That is resistance. Next question. The sodium ion concentration in the cytoplasm of a neuron will increase, decrease, or not change when its voltage-gated sodium ion channel open. The answer is A. Once the voltage-gated sodium ion open, once the channel open, the sodium will enter the cell because there's more sodium outside, less sodium inside. So every time when the channel open, first think about the concentration outside and inside the cell. Since the sodium ions outside the cell enter the cell, then inside in the cytoplasm, the sodium ion concentration will increase.